This problem is a volume to moles to moles to grams problem. You're trying to figure out the grams of sodium carbonate. And you're starting here with a volume and a concentration of nitric acid. So the first step, going from a volume to a moles, you've got to turn milliliters to liters, and then you multiply by the molarity to give moles of HNO3. So volume to moles is essentially volume in liters times moles per liter to give you moles. Then the moles to moles part, it says here that 2 moles of nitric acid are needed for every 1 mole of sodium carbonate. So you'll essentially multiply by 1 over 2, 1/2. You're starting with HNO3, so it goes in the bottom, and you want sodium carbonate, so that goes in the top. So the moles to moles part here will be multiplying by 1/2. And then finally, when you've got moles of nitric or sodium carbonate, then you'll use molar mass to get it back to grams. So volume to moles to grams. See if you can check this out. I'll try and put up here on the board here what I would do in this problem. So in this problem, you've got 25 milliliters of a 0.155 molar nitric acid solution. And the goal is to find the grams of sodium carbonate needed to react with it. And so first step, milliliters to liters. So divide 25 by 1,000 to get liters. And then the big M just stands for moles per liter. So that will get rid of the milliliters, it'll get rid of the liters, and at this point now you have moles of nitric acid, how many moles of nitric acid you're starting with. Then the balanced equation says, this part right here, 2 moles of nitric acid are needed per 1 mole sodium carbonate. So to turn my moles of nitric acid into moles of sodium carbonate, that's where the balanced equation comes in. I'll put the 2 on the bottom, 2 moles of nitric acid per 1 mole sodium carbonate. And then finally, you're trying to get it into grams. That's where the molar mass comes in. Mole of sodium carbonate, 106. So in your calculator, you go 25 divide 1,000 times 0.155 divide 2 times 106. You don't have to put any enters or anything like that, just all on one side. And if you've done it, then it comes out to be 0.205 grams. Calculators are really good. You can do all of this in one step. That's why I kind of like writing it like that. You, of course, don't have to, but it is one way that you can make yourself more efficient. Any questions on it? Okay. These next questions will be about the thermochemistry kind of stuff. And here we have a piece of copper. It's being heated, and it gives 100 joules of energy. And the temperature of the copper rises from 20 degrees to 71.9 degrees. And you can use this information to calculate the specific heat of copper. And specific heat is usually given the symbol C in these kind of expressions. This is a Q equals MC delta T. See if you can use this information to solve for C. And C will be, or M will be just grams. You don't have to turn it into moles. Delta T, final temperature minus initial temperature. So the only thing you shouldn't have then is the heat capacity. Heat capacity is always a positive number. So heat capacity is an interesting number. It relates how much energy it takes to raise 1 gram of substance by 1 Kelvin or 1 degree Celsius. Smaller numbers mean that the substances will heat up faster, and bigger heat capacities mean the substances will heat up slower. So water, 4.184, is one of the higher heat capacities. It takes more energy actually to heat water up than it does most things. Most metals have heat capacities less than 1. All heat capacities are positive. So answer E here doesn't make any sense. But anyway, to figure this out, Q is literally just the joules, the energy transferred. So Q here is literally 100 joules. The M is the mass, 5.00 grams. We're looking for C. Delta T, final minus initial temperature. So this copper started at 20 degrees and ended up at 71.9 degrees. So final minus initial. Notice we never needed the time here. Time is usually for kinetics, which is something we haven't done that much with yet. So in this problem then, you'd solve for C. C would be Q over M delta T. So it's pretty much just plug and chug. 100 divided by 5, and you would also divide it by the difference between those two, or 51.9. And again, as long as you get a positive number, that's good. 0.385 is the heat capacity here. Your delta T, I would use Celsius here. You can use Celsius or Kelvin. So because I gave you Celsius values, I would just throw them in as Celsius right there, but there would have been nothing wrong with going to Kelvin if you wanted to. The positive sign means the energy is being absorbed. It will see some negative Qs, negative delta H's and stuff, and that means energy is being released by the system. So this copper is gaining energy, that's why its temperature is going out. Any questions on that? Here's a question. We've got some water. It's starting out at 22.5 degrees Celsius and 108 grams. And we're mixing it with some more water, 65.1 grams, but we don't know its temperature. We didn't measure it, forgot to measure it. But when all is said and done, the final temperature of the two waters mixed together, 47.9. See if you can use this information to calculate what the initial temperature was of the other water. Now, remember that hot plus cold always equals warm. 22.5 is the smallest temperature, and it's less than the final temperature of the two being mixed together, all right? So will your initial temperature be less than, equal to, or greater than 47.9? Greater, well done. Something hot, something greater than 47.9 is being mixed with something cold, and the final temperature is the warm temperature. So your answer here is going to be a number larger than 47.9. Answer A probably doesn't make a lot of sense. So use this as a guide then to figuring out what it is. These problems are like algebra, and it's not that hard, but they're kind of annoying, and I understand completely. If you have a solve button function on your calculator, you can absolutely use that here. But if you don't, it's totally fine. The goal is you have a TI. This is like Q hot plus Q cold equals 0. And each Q hot and Q cold is its own MC delta T. So for water, MC delta T hot plus MC delta T cold water equals 0. You can also have Q hot equals minus Q cold, something like that, and that's fine too. But anyway, what I did up here is I just substituted all the different values. And you want to solve for the initial temperature of the hot piece. And again, remember, it'll be a number larger than 47.9. More than that, it's hard to say what it is right now. 4.184 is the heat capacity of liquid water, a number we'll use quite a bit. On a problem like this whole part right here is just a number. So figure out what it is right away and throw it on the other side. So what was a positive number will become a negative number, and that's fine. Then what I would do is you can divide by these two over here, which is just a number. So you'll have 47.9 minus TI equals some number, all right? And then the goal is just to get TI by itself. You can also distribute a property whichever way you want. So here's the kind of boring math. In this problem, I set it up Q hot equals minus Q cold. That's fine too, doesn't matter. MC delta T hot equals minus MC delta T cold. So I just put this on the other side already. 4.184 cancels out. You have 47.9 minus TI equals a number, which in this case is minus 42.1. Get TI positive by itself, so put the numbers on the other side. 90.0 should be your answer on this problem. Okay. Any questions on that? Can liquid water, under normal circumstances, be 274 degrees Celsius? No, right on. Liquid water only goes from 0 to 100. So again, I'm trying to think about this strategically. It's not going to be this answer because that's too high. It's not going to be a number less than the warm temperature of 47.9. So that's a way to at least wipe out some of these numbers as possibilities, all right? Sometimes these things get forgotten. But of course, the ultimate way then is to go through this process. So, any questions? Yeah.
So if you use the distributive property for it too, you get the same answer?
Yes, absolutely, totally. So like you can multiply these numbers together, multiply them by 47.9, and these two numbers minus TI would give you absolutely, and you should get the same answer.
Okay.
If you do this problem and you get like 90.1, 89.9, for heaven's sakes, just pick the one that's closest to it, man, because sometimes when you do a way that's different, you will get just slight differences in that, uncertain value, the doubtful digit, okay? But it should be awfully gosh darn close. So just FYI, if your answer is close but not quite the same, you're probably okay to pick the one that's closest. And I mean that sincerely, I'm not being cynical or anything, so yeah. Freaking sig figs. Oh, did I say that? I'm sorry. Lovely sig figs, experimental science. Don't throw tomatoes at me, please. Other questions? Here's a compound, a reaction. It has a standard enthalpy of combustion minus 2,044 kilojoules. So what that means is if you take some propane, which is what this stuff is, and you burn it, like in a barbecue, you make CO2 and water, you're going to get minus 2,044 kilojoules. And notice that's minus 2,044 kilojoules per mole C3H8 burned. So if you're burning 3 moles of propane, how much energy do you think you're going to get up? See if you can figure that out based on the information. We'll talk about it here in a little bit. So this is a combustion reaction, like the ones we've seen before. You're taking something organic, you're adding oxygen to it, basically burning it, and the only products, again, CO2 and water. And burning fuels, like octane, gasoline, any of these kind of things, very exothermic. So this is a negative number. That means a lot of heat here is being released. And if you drove in a gasoline-powered car this morning, you were using the combustion of octane gasoline to make it happen. This number is per reaction. And in the reaction, 1 mole of propane is creating this much energy. And I'm getting that because there's, again, that invisible 1 right there, all right? If there would have been a 2 right there, then it would have been this number divided by 2. It would be this number divided by 5 if you're interested in oxygen, but people usually aren't interested in oxygen. So in this case, we're burning 3 moles of propane to lots of sig figs, and this much energy per 1 mole of C3H8, and we have 3.000 moles of C3H8. You basically just multiply this by 3, and it comes out to be negative 6,132. So if you see a value like this for a reaction, you just look for the reaction itself. In this case, it's 1 mole. And we're burning 3 moles, so it would be 3 times this number of energies being released. These energies are being released, they're being combusted. If I said what's the energy for forming 3 moles of propane, you'd have to reverse the reaction around, because then the reaction propane would be a product, not a reactant, a positive number instead of a negative. But that's, besides that one little trick, these are usually pretty straightforward. The book likes per reaction, and this reaction has 1 mole of C3H8. So this is more like what the book uses, which is fine too. All right, whatever way you want to do this is cool. Any questions on that? Okay, here's a reaction where we have silane, which is a compound called SiH4, silane. It's reacting with oxygen to make silicon dioxide and water. This is actually a type of combustion reaction, but with silicon. And I'd like you to find the delta H, the enthalpy for this reaction, using these values. And this is one of the times where you want to take delta H products minus delta H reactants. See if you can do that using those values given right there. So these values right here are all heats of formation, and those are the values in that table. So when you go to mhchem.org/thermo and that big thing comes up, those are the heats of formation values. And if you have all the delta HFs, then all of the delta H's that are products minus all of the delta H's that are reactants is how you solve these problems, all right? This is the summation sign. I find sometimes I draw it better than other times, so I apologize, but it just means add up all of them. So in this case, you want to add up all the delta H's of the products, the SiO2 and the 2 waters, and subtract from it all of the delta H's that are the reactants, so the SiH4 and the 2O2s. And so that's where these values come in. So the products, SiO2 and 2 waters, SiO2 is minus 910.9, water negative 241.8, and there's 2 of them here. So if there's a 2 stoichiometry, just multiply it by 2. That's the sum of the delta H's of the products. And then from that, you subtract the sum of the delta H's that are reactants. And you definitely have the SiH4, 34.3, but I did not include a value for the heat of formation for oxygen. What is the value for the heat of formation of oxygen? 0. Well done. That's right. All the elements in their standard states are equal to 0. So on a problem like this, it might be tempting to say E, not enough information, but all the elements in their standard states will be 0. So in this case, oxygen, an element in standard state, is just 0. So it's 2 times 0, essentially, which means you don't have to worry about it. So on your calculators then, minus 910.9 plus 2 times negative 241.8 minus 34.3, all right? Make sure you remember to do the minus sign by any of the reactants. And it comes out to be minus 1,428.8 kilojoules. So answer B right there. And again, here's products minus reactants. Oxygen is 0, don't have to worry about that. You will always have access to a table where I give you the values you can solve for it. Any questions on that? Is this exothermic or endothermic? Exo, right on. Negative numbers in this section always mean exothermic. Energy's being pushed out away from, given away. If this number would have been positive, it would have been endothermic. It would have been energy absorbed. Any questions, any of this stuff? Heats of formation are pretty important because that's where the table comes from. There's lots of stuff like that. So what I'd like you to do down here is define the standard molar enthalpy of formation equation for gaseous methanol, all right? And I'll be honest, it's A through D. Methanol makes you go blind if you drink it. In the days of Prohibition, a lot of the alcohol was impure with methanol. People went blind and stuff like that. That's just me being stupid. So the answer will be A through D. See if you can figure out which of those would be a good answer. All right, so a heat of formation means two things. It means, first of all, you can only have 1 mole of product, and if you look, all of these are just 1 mole. But if there would have been a 2 right there, then that would have been disqualified. All the heats of formation, all right, the enthalpy of formation is per 1 mole. And the other thing, though, is that all reactants are going to be elements in their standard states, all right? So if you look through some of these, like CH4, is that an element or a compound? Compound, right on. Compound is a mixture of 2 or more types of elements. So CH4 is not going to fly. CO is a compound. Water is a compound, all right? So those 3 are automatically disqualified because they have a compound. And the only one that doesn't have any compounds, that's not E anyway, is B. And it's carbon, graphite, hydrogen's natural form, H2, and you need 2 of them because there's a total of 4 hydrogens. This is where my feathers get ruffled, but I have nothing, I just have to suck it up. I have to have 1 mole of product right there, so that's why I'm going to use 1/2 of 2. Oxygen also is a diatomic, it comes in pairs, but I only want 1 oxygen for methanol. So because I must have a 1 right there, I will have to use a fraction right there. Fascist feet of formation equation, but anyway, that's why that one is the best answer. Any questions on that? Yeah.
So it's only 1 mole of products, not reactants?
That's right. So if you had, like, on the last problem, water, I think it was minus 241.8 kilojoules. That's saying that forming 1 mole of gaseous water from hydrogen gas and 1/2 oxygen gas will give you negative 241.8 kilojoules. Yeah, it's always based on the product. The reactants, if they're all elements, have values of 0, all right? So you don't have to worry about the reactants is what it comes down to. Just worry about the products. Excellent question. Good. Other questions? Okay. This last question is an example of Hess's law, all right? So it says to calculate the standard molar enthalpy of formation. Formation means 1 mole of product, all reactants, elements in their standard states. So find the delta HF for iron 2 chloride using these 2 equations, all right? And you'll basically use like a type of Hess's law expression, but you do need to figure out what equation you're looking for. And remember, heat of formation, 1 mole of product, all reactants, elements in their standard states. See if you can figure this one out, and we'll talk about it here in a little bit if you get stuck. Remember, it's iron 2 chloride, FeCl2, not iron 3 chloride. So in this problem, the first thing to do is to figure out the desired equation that you're looking for. In Hess's law problems, you've got to know like what you're aiming for. And this is another heat of formation equation. So again, when you have a heat of formation, the two things to pay attention to: 1 mole of product, so FeCl2 will be your only product, and the reactants will be elements in their standard states, and that way you don't have to worry about their enthalpies and stuff. So iron 2 chloride has iron and chlorine. So over here, you write Fe and Cl2. Because chlorine and diatomic have no fear of ice clear, Bru is one of the diatomics. Iron is by itself, it's not one of the 7, so it's there. And when you look at it, everything is balanced. So 2 Cls, 1 iron, 1 iron. So this is the equation that you're looking for in this problem. Any questions getting to this part? So now the goal is just to take these two expressions and get it to look like this. And there's iron 2 chloride and iron 3 chloride. And obviously in our expression, we don't want any FeCl3. We want it to cancel out. And the other thing is we want iron 2 chloride, which only appears in the first reaction, by the way. We want it as a product, not a reactant. So let's take this expression and flip it, all right? And that's going to do two things. Most importantly, it's going to put iron 2 chloride on the product side. So when you flip it, you would write FeCl2 plus 1/2 Cl2 as your products now, not reactants. And then iron 3 chloride, FeCl3, would be your product. What do you do to the sign of delta H when you flip a reaction around? Flip it, that's right. Negative becomes positive, positive becomes negative. So this negative 57.7 becomes a positive 57.7 kilojoules. When you flip a reaction, you just change the sign, all right? Change the sign, positive, negative, negative, positive. Is that clear? Any questions on that part? Now, at this point, all right, hopefully we'll be able to add these two together and end up with just Fe plus Cl2 making FeCl2. So when you combine things, just like with spectator ions or whatever, if something's on both sides, they cancel out. You could subtract FeCl3 from both sides. So FeCl3 is on both sides, so that's out of there, and that's good. We don't want that anymore. We also have 3/2 Cl2 and 1/2 Cl2. So this is like 1.5 and 0.5. So we can combine these two. If you subtract half a chlorine from both sides, then 1.5 minus 0.5 is just 1. So we're left with iron, which is good. That's by itself, and we want iron. 3/2 minus 1/2 is 2/2 or 1 Cl2, and that makes FeCl2. So by flipping the iron 2, iron 3 chloride equation around, everything cancels out, and we're left with our heat of formation. And then the delta H for this reaction would just be negative 399.5 plus 57.7, and that comes out to be negative 341.8 kilojoules per mole. So this is how Hess's law works, all right? You always have some kind of desired equation. In this case, we figured it out. Sometimes it's given to you. You can then use the equations that are given to you to try and make them look like that expression. And in this one, we flipped the iron 2, iron 3 chloride reaction around to make everything else cancel out. If you flip the reaction, you change the sign. The only other part about Hess's law is if you multiplied a reaction through by 2, you would multiply delta H by 2, that kind of stuff. Those are the only two tricks of Hess's law to figure out what's happening. Any questions on any of this? All right. So between here and Wednesday, all right, start looking at the exam prep, all right, see how you do. On Wednesday, we're going to have just another review day, and you can ask me questions on anything. You can ask me questions on S's Law or stuff like that. We'll go through some problems. Should be pretty fun. Don't throw tomatoes at me. All right? All right. Thank you for being here. Have a good day. I will see you on Wednesday.